Okay, so today we're going to do sort of a collection of tricks. Some of them are, the first set are basically tricks for trigonometric integrals. Tricks for trigonometric integrals. And then the second set are what are called trigonometric substitution. Okay. It's basically a particular form of U substitution. Okay. And then the last is something called rationalization. Rationalizing substitutions. Okay. So these last two are basically some particular form of U substitution, and then the first one is just a collection of minor tricks. But although they're minor tricks, you tend to use them. Some of them you use a lot. Okay. Okay. So let's do some examples. So the first set of tricks are kind of specific. They only work in certain situations. So let me show you what I'm talking about. So here is the integral of cosine cubed. Right? Somebody asks you to integrate cosine cubed. How would you go about doing it? So what we're going to use is the so-called Pythagorean identity, right? That sine squared plus cosine squared equals 1. Okay. So you remember, back when you learned about sine and cosine, the sine and the cosine and the sine were if you had some angle, then the cosine and the sine were the x and y coordinates of this particular point on the unit circle, right? That this thing here was cosine theta, this thing here was sine theta, this thing here was sine theta. Okay, so this is, I don't know if this is how you think about cosine and sine, but this is the right way to think about cosine and sine. That cosine and sine, cosine of theta is the x coordinate of this point on the unit circle that you get by drawing a ray out from here at an angle of theta, right? So if I'm talking about the cosine of pi, right? If I'm talking about the cosine of pi, I'd say, okay, I'm going to take the ray at angle pi, right? And I'm going to look at this point of intersection with the unit circle, and I want the x coordinate of that, right? So, right, cosine of pi is the x coordinate of that point. Well, that's going to be -1, right? Sine of pi is going to be the y coordinate of that, and so that's 0, right? Okay, so this is the relation between cosine, sine, and the unit circle. Yes. That is what it is. Okay. Yeah, I'm not sure why we have this glorious music in the background, except that this is pretty important. Okay. Okay. So, right. So then, sine squared plus cosine squared, right, is the length, is the distance to 0. So that's always going to be 1, right? Right. Cosine squared plus sine squared is going to give us this thing squared, but this is the unit circle, so that's always going to be 1, right? So cosine squared plus sine squared is always 1, and that's called the Pythagorean identity. Okay, so we're going to this thing, if you just look at it by itself, maybe not so obvious how you would integrate it, right? You say, okay, I'm going to use the Pythagorean identity. I'm going to replace I'm going to think of this as cosine squared times cosine. Okay, cosine squared times cosine. And I'm going to replace the cosine with 1 minus sine squared. And so I get 1 minus sine squared, 1 minus sine squared cosine. Right. And so you end up with the integral of cosine minus sine squared cosine dx. Right? Okay, everybody all right? Okay. And so what's the antiderivative of cosine? Sine. Right? What's the antiderivative of sine squared cosine x? Take 30 seconds and do this. Write down the answer for this part. What's an antiderivative of this? Or take 10 seconds. Right? You're going to do this by using a u substitution, right? Or just by looking at it. Right? What are you going to take as your u? Sine, right? You take u as your sine. Maybe I'll turn to somebody nearby and talk with them about your answer. Okay, so what's the answer for this? The antiderivative? Somebody just say it out.
Is it 1/3 sine cubed?
1/3 sine cubed, exactly. Right, so sine cubed over 3. I'll get some concept. Okay, and if you weren't so confident about how you do this part, you say, okay, I'm going to take my u to be sine, my du then is cosine, right, cosine dx, right? I change this to u squared du, right? Use the u substitution, take the antiderivative, right? And then you switch back to x, the x variable. Any questions? Any questions? Okay. Okay. So here's another one along the same lines. You've got sine to the 5th cosine squared. Sine to the 5th cosine squared. Okay, so one way you could do this is again by using the Pythagorean identity. So you say, okay, I've got sine here times sine to the 4th. Got a sine to the 4th. Okay. Then you see what I'm going to do? What am I going to do? What's that?
Would be 1 minus cosine x.
1 minus cosine x
And then the rest
squared. squared, right? Because I've got it to the fourth, right? So I've got sine squared squared, so I'm going to replace that with sine squared squared, right? Right? This sine to the fourth is sine squared times sine squared. In other words, 1 minus cosine squared times 1 minus cosine squared. Okay. And then you'd say, okay, well, this is sine x. I've got this 1 minus 2 cosine squared plus cosine to the fourth cosine squared x dx. Okay, take 1 minute and finish it up. Turn to somebody nearby and talk with them, please. You multiply it out, right? And you say, okay, and then you use your use substitution, right? So this is going to be, what's this first part going to turn into? Can somebody tell me? Mr. L?
I'd say negative cosine cube x over 3.
Okay, negative cosine cubed x over 3, right? Because you take your u to be cosine, your du is going to be negative sine, right? And then you do the rest in a similar manner, right? So you say you get plus cosine to the 5th plus 2 cosine 5th over 5, right? Plus cosine to the 7th over 7. Minus 62. Okay, very clear.
I don't understand why I understand how you arrived at the answer, but how you chose which part of the original equation to substitute.
Yeah. So think of what would happen if I switched this cosine to 1 minus sine squared, right? I guess you could do it that way, right? You'd say, I get 1 minus sine squared, right? Okay, so let's see what happens. I don't know, maybe it doesn't, maybe it's fine. So you get sine to the 5th 1 minus sine squared dx, right? In other words, you get sine to the 5th x minus sine to the 7th x dx. Okay. Right? And then what would you do? You could probably keep on going, right? What would you do at this point? You could play the same trick as we have, right? You've got sine to the 4th. You replace that with 1 minus cosine squared squared. You've got a sine to the 6th here, 1 minus cosine squared cubed, and you'd end up doing something similar. Okay, but yeah, you're right. You're right. You're absolutely right. We could have gone a different route. Okay. 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 Is that okay? Everybody got any questions?
What are the signs that you're supposed to change, like using the trig identities?
I'm sorry. Start over. Say one more.
Like, what are the signs to know that you're supposed to change, like using trig identities for like Pythagorean identity?
Yeah. So. Right. So, yeah, exactly. So this trick only works in certain cases, right? And you're wondering under what circumstances, right? So you say, okay, well, look at this thing. I want to have a sign left over at the end, right? Without my sign left over at the end, if this were an even power, then switching it over to sines would just give me powers of cosine, right? But so what I see when I look at this is that, look, if I break this up into sine times sine to the 4th, and I switch this sine to the 4th into 1 plus cosine squared, then I'm going to have powers of the cosine times the sine. That's good, right? Do you see that that's good? Because that's good because I'm going to take my u as cosine, and then I've got my du sitting here, right there. Okay. So that's how you, if you see something like this, some odd power of the sine, right? Odd power of the sine against powers of the cosine, then that's your cue, right? Or vice versa, right? Some odd power of the cosine against any power of the sine. Yeah. Okay. And then this trick might not work otherwise. Yeah. Right. And that's the same sort of thing with the first example, right? You've got some odd power, right? And you say, okay, well, if I switch 2 of these powers to sines, I'll have a cosine left over. I'm sorry, I'll have a cosine left over, and then I can use as my du. Okay. Yeah. So I mean, if you look in the book, it will give you like what to do in this case, what to do in this case, what to do in this case, what to do in this case. But I have to say that these sorts of tricks aren't in general all that useful. So I'm only going to show you a couple of them. One trick that actually is useful that you'll see a lot of is the following. What happens if you have sine squared? Okay. For this, use a trigonometric identity. You say, okay, sine squared is actually the same thing as 1 minus cosine 2x over 2. So you just use a trig identity. Right, so there's a trig identity, there's a pair of trig identities. Sine squared x is 1/2 1 minus cosine 2x. Cosine squared x is 1/2 1 plus cosine 2x. Okay, so these just memorize them. They're handy. They show up a lot. Okay, right. So you got this. You got your 1/2 integral cosine, right? this, right? And so take, hold on, you guys are still ready? Okay, so take 30 seconds and integrate this, find the antiderivative of this. Yes. The antiderivative of 1 minus cosine 2x. This is strange noise I keep on hearing. Okay, it's all right. It sounds like, sort of like a lightsaber, actually.
Yeah, I can't really explain it much. Just happens.
That's all right. It sounds like my son's lightsaber toothbrush. Who's brushing their teeth back there? Okay, so you get 1/2. Of course, the 1 turns into an x, right? What about the negative cosine 2x? 1/2 sine 2x. Right? Because when you differentiate this, you're going to get cosine 2x times 2. Right? And so you end up with, 1/2 x plus 1/4 sine 2x plus the constant.
Can you explain the 1/2 again?
This 1/2?
Yeah.
Yeah, right, because you're integrating negative cosine 2x, right? You're integrating negative cosine 2x, so you take your u to be take your u to be 2x, right? Your du is 2dx, right? And so this turns into negative cosine u times 1/2 du, right? So far so good?
Yeah.
Okay. So you've got negative 1/2 integral cosine u du. What's the antiderivative of the cosine? That's just going to be sine, right? So you get negative 1/2 sine u plus constant. In other words, negative 1/2 sine 2x plus constant.
Should be negative on the original problem.
I'm sorry?
Should be.
Oh yes, there should be a negative here. Sorry. X. Thank you. Okay, so that, integrating cosine sine squared or integrating cosine squared, use the trigonometric identity. Yes.
Suppose I get sine to the 4th. Would it be useful to do it that way?
Yes. See, so if you get sine to the 4th, right, then you would get this thing squared, right? You get this thing squared, so then you would have a cosine squared. Then you'd have to use this thing and switch it over to cosine of 4x, right? And then you go on. Okay, so yeah.
Even powers.
Yeah, so for even powers, this is the trick. Yeah. But like I said, I'm not, you have some of these things on the homework, but it's not a particularly useful skill to be the master of these, these sort of special cases of trigonometric integrals. Okay. But this trick that we've just shown you turns up a lot, so please do know it. So there's one last thing that One last common trick that how do you integrate the secant? Anybody know how to integrate the secant? Maybe you saw this in high school. How do you integrate the secant? The answer is kind of funny. You multiply by 1. You multiply by a funny looking 1. Anybody know it? Anybody know the trick? Sorry?
This is secant x plus tan x.
Yes, yes. So you say, I'm going to multiply this thing by secant plus tangent divided by secant plus tangent. Okay. So you throw in this funny looking 1. It's always okay to multiply by 1. So you multiply by this. Of course, you get secant squared plus secant tangent over, let me write it this way, tangent plus secant, just to make it more suggestive. Okay. And then you notice something, right? What do you notice? Anybody see it? You notice a relation between the top and the bottom, between the numerator and the denominator. Right. The top is the derivative of the bottom. You've got u prime, and you've got u here. Right. If u is secant plus tangent, well, du is secant squared plus secant tangent. Right. So this is just du over u. Right. This is du over u. When you integrate it, you get the natural log of the absolute value of u. Anybody have questions about that? Any questions? Any questions? Okay, so like I said, this is these tricks. You're not going to see that you're not going to see them that often, but every once in a while you may see this. What seems to turn up a lot is the previous set of identities in integrating sine squared and cosine squared. Those are probably the most common ones that you'll use. Okay. A better set of tricks is the next, called trigonometric substitution. And this is again based on the Pythagorean identity. So cosine squared plus sine squared equals 1. So remember the Pythagorean identity, cosine squared plus sine squared equals 1. Okay. And if we divide everything by cosine squared, right, divide everything by cosine squared, we get 1 plus sine over cosine squared, that's tangent squared, equals 1 over the cosine squared, well, that's secant squared. Right? So we also have this Pythagorean identity. Right? Just divide everything by divide the whole identity by cosine squared. So 1 plus tangent squared is secant squared. And trigonometric substitution basically is dealing with terms that look like plus or minus x squared plus or minus a squared. Okay, where a is some constant. x is your variable, and a is the constant. Okay, so let's start off with an example of that. So, example. If I ask you to integrate this, the square root, 1 over the square root of 1 minus x squared, okay, then you can do it using so-called trigonometric substitution. So here's how you do it. You say, well, notice that x lies between, x lies between 1 and -1, right? If I'm looking at the square root of 1 minus x squared, well, I don't want 1 minus x squared to be 0 or negative, right? It's between -1 and 1. Okay, so okay, so what we're going to do is we'll let theta be the arcsine. I'm sorry. Yeah, the arcsine of x. Let theta be the arcsine of x. Okay. Remember back when you had the sine function, right? So here's the sine. When you had the sine function, right, and you wanted to invert the sine function, the way you did it, you can't invert the whole sine function. What you do is you restrict the sine function, because the sine function is many to one. It's not a one-to-one function. You can't invert the whole sine function, right? So what one did was you constrain the sine function to just this part, right? -pi/2, right? Right? And you said, okay, I'm going to pretend I'm only going to look at this part of the sine function, right? Right? And then you say, okay, in that part, the sine function is 1-to-1, and so I can invert it, right? So, right? So you can invert the sine function if you restrict theta to -pi/2, pi/2. Okay, and you get this sine inverse function, right? Sine inverse function is going to go from -1, 1 back to -pi/2, pi/2. Right. So this is a big recall. Right? Recall what the inverse, how we made up the inverse sine function. Okay. Right. Okay. Okay. So so here our x lies between -1 and 1. So we let theta be sine inverse x, right? It makes sense. We can talk about the sine inverse. Right? Sine inverse is defined on -1, 1. Our x lies between -1 and 1. And so we said, okay, let theta be sine inverse x. Okay, right? Because then, notice that then theta is going to lie between -pi/2 and pi/2. Okay, everybody all right? Everybody all right? Ayun.
I was getting confused, but I'll figure it out.
Okay. So we've got this thing. We've got this thing here. Okay. And we say, let x be sine theta. Okay. I'm just saying, I'm going to say it the same way, right? So
Yeah, and why do
x
we
be
choose that
sine theta.
Why do we choose sine theta?
Why do we choose sine theta? You'll see in a second. Okay. Let x be sine theta, right? Where theta is going to be between negative pi over 2 and pi over 2. Okay. If you don't want, if you like sort of have an aversion to the inverse function, you can write it like this. It's the same thing, right? Right? Theta is sine inverse x, sine theta is x, right? The same thing. Okay? Let x be sine theta. Okay. Then dx is what? Dx is what? Cosine theta d theta, right? Cosine theta d theta. Okay. And so when I do my substitution, right? When I do my substitution, I get dx, right? So I get my cosine theta d theta. I get 1 over the square root of 1 minus sine squared theta. Okay. Okay, and maybe now you see why we chose x to be sine theta, right? Remember, cosine squared plus sine squared equals 1. So 1 minus sine squared is what? Cosine squared. Right? 1 minus sine squared is cosine squared. And so this thing changes into 1 over the square root of cosine squared. Okay. Why do we choose sine squared? Because 1 minus cosine squared, 1 minus sine squared is cosine squared, and so we get the square root of a square. Right? What was troubling us about this was the square root. Okay? And we use the Pythagorean identities to change this thing into a square, so we end up with the square root of a square. That's the idea. Use the Pythagorean identity to get rid of the radical. Okay. Right? Use the Pythagorean identity to get rid of the square root.
You don't further simplify that.
So, we're not done yet. We're not done yet. Okay. Okay. So, by the way, notice that we could have used x equals cosine here, right? That would be just as fine. We would end up with the square root of 1 minus cosine squared. That's the square root of sine squared. Okay, we could have done that. Okay, but we wouldn't want to use secant. We wouldn't want to use secant. We wouldn't want to use tangent. Okay, right? Those wouldn't help us. Okay. Okay, let's come back here. Okay, so now we've got the 1 over the square root of the cosine. Well, the square root of the cosine, the square root of cosine squared is the absolute value of the cosine. Right? So we're not completely off of the hook yet. Right? Yes, Catherine?
Where did that additional cosine theta come from?
That is our dx. X is sine theta, dx is going to be cosine theta d theta.
Okay. So what substituting?
Okay. Okay. So we get absolute value of the cosine, but the good thing is that, look, the theta lies between negative pi over 2 and pi over 2, right? So the cosine is the x coordinate, right? We're over here, and the cosine is the x coordinate. So it's always going to be positive, right? Cosine is the x coordinate, you know, all the cosines on this side are positive, right? All the x coordinates on this side are positive, right? So we can get rid of the absolute value signs, right? This just becomes the integral of d theta, right? So we get theta plus c. Okay. Theta plus c. Now we switch back to our original variable and write this arcsine plus c. Right. Theta, remember, theta was the arcsine of x. Right. So we get arcsine x plus c. And so we get this nice formula, right? The antiderivative of 1 over 1 minus x squared is the arcsine.
And this is something you have to memorize.
No, you have to understand. Yeah. Well, so this is our first example of a trigonometric substitution. I've got loads of other examples that we'll do next time. Okay. By the time we get through them, you'll say, okay, you'll look at this thing and you say, okay, yeah, I need to substitute this thing with the sign, and then work it out. So the only thing you need to remember is actually the Pythagorean identities, right? And you don't even have to remember the Pythagorean identities. You have to remember, if you don't remember the Pythagorean identities, you just remember that these guys are the x and y coordinates on the unit circle. So if you know this, then basically everything else follows from there. Yeah, this gives you the Pythagorean identities. This thing will basically cue you as to what substitution you need to make here. Okay. But I'll make that clearer next time. We've only done the first example. Okay, that's it for today.